In this lesson, we're going to talk about nested triangles or side splitters. And it's actually important that we go back and look at a do now question just to refresh our memory here. So remember, when we had parallel lines, if we slid this down using a transformation, this 42 would be right here, the exact same, because those are corresponding angles. They're in the same spot with those parallel lines. Same thing with this 87. If I slid it down, if these lines are parallel, this is also got to be 87. And then I could use that triangle for the three blue angles, right? That makes a triangle. So we know 180, I'm going to take away 87 and 42 using the triangle sum theorem here. This last angle's got to be 51. So remember, those two angles are corresponding because those lines are parallel. They got to be equal. Same with the 87. Then I use the triangle sum theorem at the end. So we're going to talk about triangles inside each other for this lesson and how we can use those corresponding angles to help us use similar triangles. So the first thing we did was just looking at two triangles. If we put them inside each other, those two angles match up. This side is parallel to this side. What if I moved it over here? Those angles match up. This side's parallel to this side. If I put this angle here, it matches up. Those sides are parallel. So when triangles are inside each other, the opposite sides got to be parallel, no matter what the triangles look like. As long as they match up with those three angles, those sides have to be parallel. So they will make similar triangles. So if lines are parallel, the corresponding angles are congruent. So there are two similar triangles. Now there's that little triangle that everyone can see, MNB. That one's easy for people to see. And then the other triangle is the whole thing, ACB. ACB. So those are the similar triangles because angle A is corresponding with angle M, and angle C and N are corresponding. And then angle B is the exact same angle in both triangles, so that has to be the same. So all three angles are the same, so they're similar triangles. So we can use all the properties of similar triangles we've talked about so far this unit. So if I want to find the length of AB here, and I want to find B prime or BB prime, I got to find these two sides. What is really helpful is to separate the triangles and just set up a proportion. So since these lines are parallel, we know the triangles are similar because these angles are the same because they're corresponding. So I have two triangles here. I have A prime, B prime, C prime, and that side is 5, 7, 6. That's this triangle that I just drew out. And then the whole big triangle, this is the harder one. C to A is 9, right? There's a 3, there's a 6, so that whole side is 9. Then A to B is X. And that missing side is Y plus 7. So now we're going to find the missing sides. And it really helps, and that's why there's this screen here, to draw them separately so we could set up a proportion. So I see 6 and 9 are corresponding, so I'm going to do 6 divided by 9 is equal to 5 and x. So I went 6 to 9, 5 to x. We got to go to the same way. If I start with this triangle, I got to go to this triangle. So 6 over 9, 5 over x. Set up that proportion because these are similar triangles. 5 over x. Then I could cross multiply and solve. 6x equals 45. If I divide 45 divided by 6, let's see what we get. 7.5. So that missing side was 7.5. Now, I want to find this side up here, y. Now, I could use my triangles and set up my proportion again. I'll have a y plus 7. Might be a little harder. But I could just see that's half of 6. So this is going to be half of 7. Half of 7 is 3.5. So if this side, b to b prime, is 3.5, the whole thing has got to be 10.5.